Hello everyone, welcome to the second morning session, Interactions Between Tropospheric Chemistry and Climate. Our first invited speaker is Drew Schindel.
Good morning everybody. I wanted to talk a little bit about maybe some thoughts rather than insights here. I'm not quite sure how insightful this will be, but some different things we've been looking at with some colleagues at GIST, but also related to some of the work as part of the ACMIP project. And one of the basic questions that I'm, in the long term, trying to get at is how much does a pattern like this really matter? So this is our estimate from the ACMIP analysis of the historical forcing due to all anthropogenic changes. So this includes greenhouse gases, ozone, aerosols, etc. And what you can see there is while the planet has experienced, the global average is up in the upper right, about 1.5 watts per meter squared, positive forcing. Some areas, especially over very bright surfaces like the Sahara or up in the Arctic, have experienced more than average radiative forcing. Some areas, the aerosol negative forcing has been so large, like over East Asia, that the net forcing, even when you add in greenhouse gases, is still negative. Well, the question really is, does this matter? Does this mean that Southeast Asia is going to cool because it has negative forcings, or does it not matter? Just going back a little bit from some of the analysis we did some years ago trying to look at this in the AR4 generation of models, this shows on the left the spatial pattern of aerosol forcing in the 20th century from 4 of the AR4 models, and on the right column the pattern of response. And the details there, I'm sure you can't see, but they're not really important. The point here is that at small scales, you don't see a close match between the patterns in those two columns. But at some larger scales, there's clearly more aerosol negative forcing in the northern hemisphere in all 4 models, and there's clearly more response in the northern hemisphere in all 4 models. So there is some relationship, but it's clearly not a one-to-one relationship, and it's not so immediately obvious exactly what that relationship is. So back in 2010, colleagues from these 4 different modeling centers, we developed some statistical analyses to try to quantify the length scale over which you saw a strong effect of aerosol forcing. And that was about 3,500 kilometers in the meridional direction and very far, at least 12,000 kilometers in the zonal direction. When we've tried to look at the CMIP-5 models, I'm not going to go into the details of what quantification measure we've used, but what we found is something like this for a length scale of the response. That thick black line is the ensemble mean from 6 of the CMIP models, and you see that kind of 1 over E folding distance is around 4,000 kilometers. That's the typical length scale over which the forcing appears to be closely related to the response. But those individual lines show individual models within the CMIP ensembles. And what you see there is that this really is not a very robust relationship across models. Some show very, very, very strong relationships, say 1,000 kilometers away from where the forcing is. Those ones that are up high there in the gray. And there's one down there that shows virtually no relationship whatsoever. So really, even if you knew the forcing exactly, which of course we don't, you don't expect the models, you'd expect a large divergence in the regional response to a regionally inhomogeneous radiative forcing, and that's really not a robust feature yet across these different climate models. One of the things we tried to do at larger spatial scales is this shows some results from a paper from a few years ago where we imposed forcings in specific regions and looked at the response in specific regions. And what you can see, excellent. What you can see here, for example, this middle panel is the response in the northern mid-latitudes, and the response to forcing in the southern extratropics is very weak, and the tropics is kind of middling, and if the forcing is imposed locally, it's much, much stronger response. So at larger spatial scales like this, there really is a strong response, strong dependence of the response, and in the tropics, which is up on top here, very little dependence on the response to where the forcing is located, but in the northern mid-latitudes or in the Arctic, you see that those regions in the extratropics are much more sensitive to local forcings then to responses. And so one of the things we tried to do was see if you could develop some fairly simple metrics that would allow you to bring into play this large regional scale response. So not down to, say, continental, national scale, but throughout a latitude band spanning much of the hemisphere. And we called this an analogy with the global temperature potential, the regional temperature potential, and an evaluation of that we published earlier this year looks again at GCMs from the AR4 generation of models. But what's shown here is that if you take this absolute regional temperature potential and you use that metric to evaluate what the response is and you compare with the actual response, most of these models, it falls fairly close to the 1-to-1 line. These dashed lines are about 20% difference, and you've got a couple cases, especially at very high latitudes, where it doesn't work too well. But predominantly in the tropics and in the northern mid-latitudes, there's enough robustness to the response that you can provide some regional information, even with a simple quantitative metric. In the new CMIP-5 transient simulations, I haven't really completed the analyses of these yet, but we've seen a few interesting results that I thought might be kind of interesting to share thus far. One thing is if we look at the difference in the two hemispheres, just in response to well-mixed greenhouse gases, you get about half again the response in the northern hemisphere that you do in the south. And that's sort of reasonable based on the greater area of land, which responds more rapidly to transient forcing, and the greater area of snow and ice cover, which can kick in these powerful snow and ice albedo feedbacks. When you look at the response to aerosol forcing, or actually we've looked at anthropogenic non-well-mixed greenhouse gases, which is largely aerosols, but also ozone and land use and such, you find that that ratio is a bit larger. So what this is saying really is that the difference in the response of the two hemispheres is primarily due to the northern hemisphere being more sensitive, at least in the transient sense, but that there is really a noticeable impact in this hemispheric asymmetry due to the location of the radiative forcing. If you look at what this does then to global mean, you see that the aerosols induce a larger temperature response per unit radiative forcing, primarily because they are mostly located in the north where you have this greater climate sensitivity. So if you think of this chart, which compares the global mean radiative forcing in historical time periods, say from the AR4, that does give you the relative magnitude of the global mean forcing. But given that the aerosols are pushed into the northern hemisphere, which is more sensitive, it's underestimating the relative contribution of aerosols to global mean temperature change. The other thing we tried to look at thus far is the difference between the response of land areas and the response to ocean. And when you look at well-mixed greenhouse gases, again, the land responds much more quickly, so not surprisingly, you get a much larger response. But when you look at the response to aerosols, the models are really all over the place. And part of the reason here is that the aerosol forcing is highly dependent upon the indirect effect of aerosols on clouds, which can, in some models, be extremely powerful over the oceans because they're relatively clean, and so you add even a little bit of aerosols and you get a very large indirect cloud response. And so those models have a larger indirect forcing over the oceans than the land, and some models are the other way around. There's more aerosols from anthropogenic activities over land than over ocean, and so it's also plausible that you might have a greater forcing over land. And so that difference in the models leads to a very large difference in the forcing, and again, this very large difference in response. So like with the length scales, we're not finding very robust patterns in the response to inhomogeneous aerosol forcing. The last thing I want to say about the forcing and the response is that this isn't really so much the response, but in a very memorable paper, Jeff Keel looked at the aerosol forcing in an earlier generation of climate models and showed that the aerosol forcing was inversely correlated with the climate sensitivity, so that it was a shape kind of like this, and models that were more sensitive had imposed more more negative aerosol forcing in order to match the 20th century historical record. In the CMIP-5 generation of models, that no longer seems to be the case. There's no clear correlation at all between the climate sensitivity in the various models and the aerosol forcing. I think these models are much more complex, much more sophisticated, and it's not really very easy to even adjust the aerosol forcing to get some a priori answer you might want. What this leads to, instead of models having adjusted their aerosol forcing to match the 20th century temperature change, is now not having done that, many of the models don't do so well at matching historical temperature change. And there's clearly a relationship between the imposed forcing, which is shown in the vertical, and the temperature response, but some models are not warming enough and some are warming too much. And so now we have probably a more realistic representation of what we think the physics really is, but it makes it harder to just tune a knob very simply and get the right answer. I'm going to switch for the last few minutes here and talk about precipitation, one of the other things we've been trying to sort out a little bit. And there have been a lot of very nice studies from Ming and Ramaswamy, looking at the GFDL model, the response to aerosols, greenhouse gases, and both put together. And these push the tropical precipitation into or out of the cooler hemisphere into a warmer hemisphere. So greenhouse gases pull the precip into the north, aerosols push it into the south. But the interesting thing is when you put them both together, the aerosol effect is much more powerful than the greenhouse gas effect. And a complicating factor is from another study, Chung and Seinfeld, is that the aerosols have both warming and cooling components. So the aerosols can, in principle, push the tropical precip either direction. So understanding what the aerosol forcing is important, understanding these very large-scale tropical changes, which have to do with how far the IPCC moves back and forth during the seasonal cycle. But as you get to very smaller regional scales, it gets even much more complicated. And what we looked at from our AR4 model is that the response to CO2 in blue and the response to sulfate in black carbon for equivalent, say 1 watt per meter squared forcing, change in rainfall, millimeters per day, per unit positive forcing. The interesting thing here is not only is there a very different regional sensitivity, which is not surprising, as many areas, of course, have much more rainfall than others, but in virtually every case, the aerosols have a much, much larger effect on rainfall than does equivalent forcing from well-mixed greenhouse gases. So this is not going to, there's no way to really construct a nice metric that says, here's my radiative forcing, here's my precipitation response, that would work in this kind of case the way it does for temperature, because it really depends on the radiative forcing agent. And what we saw here was when we looked at observations, decreasing rainfall in Southeast Asia and the Sahel, greenhouse gases are actually giving you an opposite signal, and aerosols are giving you kind of something that's much more in tune with observations. GFDL has found something quite similar, aerosols giving you stronger response per unit forcing and opposite to the greenhouse gases. So in conclusion, I think we can say that for temperature, we're starting to understand some aspects of how radiative forcing and its distribution influences the temperature response. We can see that there's an impact of climate sensitivity, but also of the forcing distribution on the interhemispheric gradient. We can see that the global mean is also going to be influenced by the distribution because some regions are much more sensitive than others. And we can see that at large areas there is some understanding and some robustness, and we can make predictions and develop emission metrics that project what the response is going to be. But when we get down to small spatial scales, I don't think we're really at the stage where we can do that yet. When we get to precipitation, there's tropical shifts. I showed you a couple examples, but there are many more out in the literature, and I think those are fairly robust and well understood as well. But it's also, I would say, fairly robust across models that the impact of aerosols is much larger. And so the spatial inhomogeneity of that forcing really matters there, not just the total magnitude of the forcing. But again, developing a metric would be very difficult. We know that a metric based on something like radiative forcing would be good for temperature, but would not work well for aerosols and understanding precipitation. Clearly, there's a lot more work to do. Thank you.
Thank you. We have time for questions.
Sorry, did you catch that? Oh, yeah. So, yes, in our model, well, we've done experiments both with only direct and with direct plus indirect effect. And it's certainly different, but I would say that there's so many things going on when you include the indirect effect that we don't really have much confidence that that difference is meaningful or that that difference is correct, I would say. In the GFDL model, when they did their experiments, the indirect effect was dominating the precipitation changes. In ours, it's much more balanced, but I don't think we understand that process terribly well. So if I got that right, it's the effect in North America of having the different types of aerosol forcing. Some positive.
We don't have organic aerosol forcing anywhere in the sea. Not that it's easy.
Right. You know, I guess I would say that so far we do not have enough understanding really of the relative roles of these. When we put in black carbon or dust, you know, any sort of very absorbing aerosol, you can see a stabilization of the temperature profile, and this goes back to the last question too. You could see this process going on where changes in the lapse rate affect precipitation, but you also see them changing nucleation, and you see changes in water uptake by the aerosols, which affect precipitation. And so I think some of these, there are multiple effects with opposite sign. And so I think certainly we change the conclusion if we change something about our organics, which are probably underprojected, but I don't even know which direction that would go.
Let's continue this discussion later. Thank you very much, Drew. And our next speaker is Meredith Fry.
I just advance with this one. Okay. Thank you. So today I'll be talking about the net radiative forcing impacts of regional carbon monoxide and non-methane volatile organic compound emission reductions. I'd like to acknowledge the co-authors on this work, including Dan Schwarzkopf and Vaishali Nayak from the Geophysical Fluid Dynamics Laboratory, Zach Edelman and Jason West from the University of North Carolina, and Bill Collins from the University of Reading. To begin, we know that CO and non-methane VOCs indirectly contribute to climate change through their impacts on secondary species. And we can quantify this using radiative forcing. We see here how CO and VOCs contribute in an emissions-based estimate, and this radiative forcing is due to its impacts on both radiatively active gases like ozone and methane, and also secondary aerosols such as sulfate. In fact, this radiative forcing is about 16% of the radiative forcing due to CO2. But before we go on and quantify radiative forcing impacts of CO and non-methane VOCs, let's first take a look at the underlying chemistry. Here, I've shown that CO and VOCs contribute to changes in oxidants in the troposphere. In particular, there are increases in OH and decreases in hydrogen peroxide that occur. Ozone, another oxidant, but also a secondary species, is expected to decrease with CO and non-methane VOC reductions. Through increases in OH, methane also decreases, and thus so does long-term ozone. Several aerosols, including sulfate, ammonium nitrate, and secondary organic aerosols, also change with these changes in oxidants. Many studies have suggested that we might include short-lived climate forcers and their precursors in climate mitigation strategies due to the radiative forcing impacts. Several more recent studies have also suggested that these short-lived non-CO2 forcing agents could help slow the near-term rate of climate change. There also might be opportunities to include these gases in emissions trading agreements, but unlike long-lived greenhouse gases, their radiative forcing varies by location of their emissions. And geographically varying metrics, such as global warming potentials, might be needed for these gases if a single uniform GWP wouldn't work. So the main objectives of this study: first, we conduct global scale modeling of 50% reductions in anthropogenic carbon monoxide and non-methane VOC emissions from 10 world regions. Those regions are shown here in the map. We evaluate changes in tropospheric composition, surface ozone air quality, and radiative forcing due to these regional emission reductions. We use the global chemical transport model Mozart-4, and our anthropogenic and biomass-burning emissions come from the IPCC's fifth assessment report, RCP 8.5, emissions inventory. Here in the figure are the anthropogenic CO emissions by region and sector, and these are the emissions that we're reducing by 50%. You can see that in North America, South America, Europe, and former Soviet Union, a large contribution is coming from land transportation, while in Africa, India, and Southeast Asia, majorities from residential and commercial emissions. We can also take a look at the anthropogenic VOC emissions by region and sector. And here we see that solvents and land transportation are important sources in North America, South America, Europe and former Soviet Union, in the Middle East, and important contributions coming from the energy sector. We use global meteorology from the GEOS-5 model, and we perform base and perturbation simulations from July 2004 to December 2005. We fix global methane concentrations because of the short duration of these experiments, only a year and a half in length, and then we run an additional methane control simulation which allows us to diagnose changes in global methane offline and then therefore calculate long-term ozone effects. We also compare our base simulations results to several observations, and in general we find that the ozone and aerosol concentrations in our base simulation agree well with these observations. We next conduct radiative transfer modeling in order to estimate our radiative forcing impacts. We bring in inputs of ozone, methane, and sulfate concentrations from our Mozart-4 simulations, and we use the NOAA GFDL radiative transfer model, which is a module of GFDL's coupled atmosphere-ocean model, AM2. It's been used in a number of studies of both long-lived greenhouse gases and also short-lived climate forcers. We output monthly mean net radiation fluxes that allow for stratospheric temperatures to readjust to equilibrium, and we calculate net radiative forcing as the change in these net fluxes at the tropopause between each of the perturbations in the base case. We acknowledge that there's some uncertainties in our radiative forcing estimates here because we're not able to account for several contributions in the current version of the RTM. That includes nitrate and secondary organic aerosols, carbon cycle feedback, stratospheric ozone, water vapor, and also the indirect effect of aerosols. So here are the net radiative forcing impacts of the regional and global anthropogenic carbon monoxide emission reductions. You can see in general, so these reflect the changes again in ozone, methane, and sulfate, the direct effect only. Across all of these regional reductions, you can see in both hemispheres wide-scale decreases in forcing or cooling effects that are due to the global decreases in methane and also long-term ozone. Regional to hemispheric decreases in ozone cause more regional scale cooling effects. And then these localized increases and decreases in forcing over the reduction regions are related to changes in sulfate. To get a better idea of how these patterns emerge, we can take a look at the tropospheric ozone and sulfate distributions for two of these regional reduction scenarios. Here I'm showing North America and Europe's regional reduction. For tropospheric ozone, we see the largest decreases regionally to hemispherically, and then smaller decreases in the opposite hemisphere. For tropospheric sulfate, we're getting both increases and decreases in these concentrations, and this relates to the different oxidation pathways that are being affected. So in the northern mid-latitudes, we see decreases in sulfate, and those relate to decreases, or the prevalence of clouds, but also decreased aqueous phase oxidation of sulfur dioxide by hydrogen peroxide, for example. In the tropics and then also in drier regions, we're seeing increases in sulfate due to increased gas phase oxidation by OH. So from these distributions of the secondary species, we can now better understand where these, somewhat how these radiative forcing patterns come about. The localized increases in forcing over North America and over Europe are again related to decreases in sulfate, but the widespread cooling effects are due to decreases in ozone and also global methane. We also calculate global warming potentials from our radiative forcing results for CO, and these are broken down into long-term and short-term components. We also estimate a global warming potential for the global CO reduction, so that's what is shown here as the global GWP. And these are at both 20 and 100-year time horizons. We find that the regional GWP estimates are within 8.8% of the global GWP at 20 years, and then within 7.5% for the GWP 100. The largest GWP estimates are found for regional reductions in the tropics, Middle East, Southeast Asia, and India. But in general, what we find here is that there is little regional variability. Now on to the radiative forcing impacts of anthropogenic VOC emissions from the 10 different regions. We see closest to the reduction region increases and decreases in forcing, while further away, smaller decreases in forcing. And these again relate to the corresponding changes in the secondary species. We can look at tropospheric ozone and sulfate for two of these regional reductions. Here I'm showing North America and Southeast Asia. For North America, we're getting larger decreases in ozone regionally to intercontinentally, and then smaller decreases in the opposite hemisphere. For Southeast Asia's reduction, we're actually getting increases in tropospheric ozone regionally, and these are due to corresponding decreases in PAN and also regional increases in NOx that result from this particular region's emission reduction. For tropospheric sulfate, we are also seeing both increases and decreases, as we saw for the CO reductions, related to the different oxidation pathways being affected. And so we can now look at the radiative forcing results again for these two regions, seeing that those increases in forcing over North America and Southeast Asia are related to the decreases in sulfate. For Southeast Asia, also due to increases in tropospheric ozone. We calculate our global warming potentials for the VOC results, and those ranges in regional GWPs are shown at the far right. The largest estimates are for regions in the tropics and southern hemisphere, Middle East, Australia, Africa, and India. And in general, we see a lot more variability here across the GWP estimates due to VOC's shorter lifetime. We also see this slightly greater short-term component for several of the regions, like South America, Southeast Asia, and Australia. And those are due to the combined effect of not only sulfate changes, but those those regional increases in tropospheric ozone that together act in the opposite direction to the long-term component of the GWP here. So in conclusion, we are able to estimate the range of carbon monoxide and non-methane VOC global warming potentials and radiative forcings across the 10 regions. We also show that there's greater sensitivity to regional reductions in the tropics and southern hemisphere. Our estimates are on the lower end for GWPs that have already been shown in the literature. However, what we do focus on here is the variability across the regional reductions. We also show that there could be an opportunity to reduce CO and VOC emissions for climate purposes or in coordinated policies aimed at slowing the near-term rate of climate change and improving air quality. And including these gases in an agreement could provide more incentive to reduce them and may lower the costs of meeting climate goals if it's more cost-effective to take those sorts of actions. Regionally variable climate metrics, such as global warming potentials, could be used for CO and VOCs, but the error in using a single global warming potential for carbon monoxide might be small based on our results. Thank you.
Thank you. Questions?
How sensitive are your results to the background NOx concentrations and VOC chemicals?
So we are, for the VOC emission reduction results that I presented, we're still evaluating those, but I think there is some sensitivity to NOx being shown, especially where we're getting those increases in ozone in for some of the southern hemisphere reductions. Yeah.
I have one.
Sure.
Did you look at whether regional differences in the VOC mix might be responsible for some of those different regional ozone responses, besides just the background chemistry?
Yeah, I actually have not looked into the different regional mixes of VOCs, but that would be important to look at, especially since their lifetimes. The lifetimes do vary based on the different species. Yeah.
Well, if there are no further questions, then let's thank our speaker again. And our next invited speaker is Colette Hill.
Thanks. Good morning. So I want to thank the organizers for the invitation, and I'm going to talk about some work that was really led by my former student, Ashley Berg, and a research scientist working with me at CSU, Maria Val Martin. And this is work that was supported by the National Science Foundation and the National Park Service. So the theme of this session is the interactions between tropospheric composition and climate, and of course it's implicit that that's part of a larger picture of changing emissions, climate, and land use. Climate driving some of those changes, of course, in emissions and land use, the natural component. But they're also being, of course, independently changing aspects of emissions and land use from anthropogenic sources and economic factors. So we have all of these things changing simultaneously and impacting tropospheric composition with high uncertainties, perhaps in different aspects here. So what I'm going to talk about today is the impact of these changes on U.S. air quality in the recent historical past and near-term future. And I'm going to be using the global NCAR CESM model in these investigations. Okay, so the new IPCC RCP emission scenarios project very large decreases in PM and ozone precursors in the industrialized world. And I'm showing you here the example for the US. This is comparing year 2000 emissions in blue with two RCP scenarios in 2050. And you can see large reductions across the board here. We also have projections in land use change. This is showing one scenario here for RCP 4.5, showing over the U.S. A potential reforestation occurring over the eastern U.S. Of course, there's a lot of uncertainty associated with these land use change scenarios as well. But in terms of thinking about near-term air quality, this is, of course, particularly, these are very aggressive decreases, and when you compare them to the last IPCC SRES projection scenarios, there's a big difference, particularly in the near term. So it's really these emissions decreases that are going to drive the changes in air quality over the U.S. in the near term. So this is being looked at in the CMIP5 models, and I'm just going to show you a quick example from our simulations just to provide some context for what I'm going to show later. This is showing the decrease in projections of surface summertime ozone concentrations over the U.S. in the RCP 4.5 scenario. And we see large-scale decreases, 5 to 15 ppb across the U.S. And you can see that when you break this apart into the impact from anthropogenic emissions, climate, and land use, and I should highlight here that Maria has also lumped biogenics into land use here, that this is really driven by the NOx emission decreases. So we have a very strong response projected here In the 8.5 scenario, we see the same degree, really, of decrease in anthropogenic precursor emissions, but we have a little bit more compensation from the stronger impact of climate, a little bit warmer climate with stronger greenhouse gas forcing, and we also have increases in methane in the RCP 8.5 scenario that drives increases in background ozone. So we still get decreases in ozone, surface ozone in summertime through much of the US, but there may be some regions of compensation. So this is the situation with ozone. Situation with PM is also very driven by these anthropogenic emissions. And really the anthropogenic emissions are the whole story for air quality PM concerns in the US. We have very dramatic decreases in SOx and NOx, and you can see that that leads to this kind of US-wide picture, and we've separated here for the eastern United States and the western US the contributions. And in the eastern US, we're talking about, you know, in a short matter of a couple of decades, having the PM that we have at the surface in an annual mean sense. In the western US, the changes are a little bit more modest. We, of course, have a little bit less anthropogenic PM in the US, but nevertheless, we see decreases of about 1 microgram per meter cubed or a little bit more. So I'll ask you to keep that number in mind, 1 microgram per meter cubed, because I'll come back to that a little bit in terms of the western United States. One particular question or concern, of course, with PM is the role of wildfires. And Westerling, Tony Westerling and others have shown that there's this projection or this association between increasing temperature and wildfire occurrence in the western US in particular. And Dom Spracklin showed several years ago that this would have an impact on carbonaceous aerosol concentrations. This is something that appears to be underestimated in the RCP emission scenarios. There's very modest increases in wildfire emissions in these scenarios. So Maria et al., Maria had recently read this paper by you et al. From Jennifer Logan's group, where they had projected an increase of about 150% of carbonaceous aerosol emissions. So she replaced that in the RCP scenarios to look at the impact. And doing so, you see that in the West, what happens is that this potential increase in wildfire activity actually compensates for the decrease that we project associated with anthropogenic emission cleanup. So the wildfire activity and the importance of that, is going to be a big factor in the Western U.S. in terms of determining whether PM actually reduces or stays about the same. And so wildfires are really an interesting kind of aspect of this land use change, potentially driving surface air quality. So that provides the segue into thinking about other kinds of land use change. And one particularly interesting phenomena has been the recent bark beetle infestation in western North America. Bark beetles play an important ecological role. They actually hasten the demise of a dying forest. So they, exist in ecosystems, and what's been happening in the last decade or so is that the warming climate in western North America has allowed these beetles to survive the wintertime and then proliferate and expand into new areas where they didn't exist previously. And so they have started attacking healthy trees. And if any of you have spent time in the Rockies in the last few years, you're familiar with these large swaths of forest with this red color, and that's forests that have been impacted by this pine beetle, largely mountain pine beetle in Colorado, for example. And this infestation started in British Columbia, and then these beetles moved down through into western North America, and it's the largest infestation on record in North America. So clearly, that's going to have huge ecosystem impacts and impacts on carbon cycling, and that's being looked at, and we were interested in impacts on air quality. So the impacts on air quality are going to come through the fact that this vegetation is a major source of biogenic VOCs. And in particular, because we're talking about bark beetles, this is attack on pine forests largely, so we're talking about monoterpene emissions. And so the impact of the pine beetle or the bark beetle on forests and on these VOC emissions is really going to be twofold. First, we have the mortality effect, because we're killing off the trees, and so the emissions of monoterpenes are going to go down as a result. But secondly, it's been observed that when these trees are under attack, emissions of different species of monoterpenes are elevated. And this may be part of the response of the tree to the bark beetle attack. So some of these monoterpenes are toxic to the bark beetle, so they're trying to repel this kind of infestation. In fact, if I go back, this picture that I have right here is actually an unsuccessful beetle attack. So this is what's being referred to as being pitched out. So the tree will actually try and produce more pitch to get rid of these bark beetles. So the monoterpenes may be another similar kind of defense mechanism. So in the year that a tree is under attack, it's going to be emitting more VOCs as a consequence. And this is something that is tricky to get real quantitative data on. However, just recently, a group at Storm Peak made some measurements of infested trees and healthy trees and compared the relative emissions of different monoterpene species. And this is hard to read, but it's just comparing the healthy or the infested emissions for different monoterpene species, so beta-pinene, 3-carene, a few others. And they saw these significant enhancements when trees were under attack. So we based our study on their results. And what we did was we started with the land model in the CESM, which describes the vegetation distribution. So we have, we know where the pine trees are. And then we took this really sort of amazingly staggering data set that's been compiled. It's a data set of annual 1 kilometer resolved mortality of vegetation associated with beetles. And it was compiled from aerial surveys from the British Columbia Ministry of Forests and the U.S. Forest Service. So we have these maps of mortality associated with beetles over really the last decade or so. And then, so those are driving the vegetation changes in our model. Then we have, of course, VOC emissions projected from Megan 2.1. And then we apply on top of that these attack effect experimental VOC increases that have been observed at Storm Peak. So we've done that over the last decade, and I'll show here just a couple of quick time slices. This is showing the relative change in these monoterpene emissions in 2004 and 2008, and the first column here is the mortality effect. So because the trees are dying off, you see a decrease in monoterpene emissions. And then this set of panels describes what happens when you actually include this attack effect. So you actually have a compensation. In fact, you have enhanced VOC emissions as a result of that are going to change in location and timing depending on where the beetles are. So we see, very, localized hotspots, very large increases, potentially a doubling of these emissions in certain years and times. Okay, so then to get to air quality, we wanted to think about SOA. So we took, the whole prediction of the VOC emissions, and then we applied some chamber SOA yields for the specific monoterpenes that show an enhancement to the simulated VOC emission increases. So this is the same kind of figure for 2004 and 2008, and I just want to point out that the color bar here is changed, so this is now minus to plus 20%. So again, the mortality effect and then the attack effect on top of that, and you see really large regional increases in SOA that are projected. Because of the lifetime of SOA, there's a bit of a larger footprint here than the hotspots from the VOC emission changes that we saw. And we get maximum increases of 30 to 40% in SOA in the simulation. Now, as I highlighted, sort of the attack effect is very uncertain. And we had these simulations show one set of data which are based on lodgepole pine, which is probably the dominant species that is really undergoing bark beetle attack in Western North America. However, some of the measurements at Storm Peak were also made on Engelmann spruce. So because of the uncertainty in this whole process, we did the same thing looking at Engelmann spruce, using that to characterize the attack effect. And we saw much greater sensitivity. We saw a doubling of SOA that occurred when we used the experimental results based on Engelmann spruce. So that's just to highlight, I think that we need a little bit more information about what that attack effect looks like and provide some context here about how important this might be. So when we used the Engelmann spruce values, we got changes in SOA over large regions of about 1 microgram per meter cubed. And if you go back to what I was saying at the beginning, the projection through the next 50 years in Western North America, in Western US, is really a 1 microgram per meter cubed cleanup in surface PM. So this is comparable to what we're seeing as a projection over the next 50 years in terms of change. It's also very important in terms of visibility in Western North America. So In particular, I'm sure many of you are familiar with the EPA's regional haze rule, which has tried to set an objective to return to natural visibility conditions by 2064. And one of the challenges is really characterizing what is natural. The estimates from the EPA is a concentration in western U.S. of about 1 microgram per meter cubed. So if herbivory attacks and this large-scale infestation over western North America have potentially changed SOA concentrations on this order of magnitude, you can see that this is something that we need to think about in terms of achieving these kinds of natural visibility objectives. So I will just wrap up here. We've shown that near-term air quality over the U.S. is very, very likely to improve, and that's really very consistent. All the work that's being done with the CMIP-5 simulations. Arlene Fiore has a really nice paper summarizing some of those results that's just come out recently. Bark beetle infestation has really likely led to some significant changes in BVOC emissions and SOA in western North America. And the effects that we're estimating are larger than any of the kinds of predictions that have been out there for changes in SOA over the next century. So this, historical occurrence over the last decade is very significant compared to other changes that we predict in SOA. And finally, I just want to conclude that, I think really the largest changes, some of the uncertainty that we're seeing associated with these land use effects, either wildfires or bark beetles, are of course some of the big challenges in trying to actually capture those in models and predict those with any certainty. And I think that's an underlying, very important uncertainty in all of our chemistry climate projections going out into the future. And with that, I'd be happy to take any questions. Thanks.
Thanks. We have time for a couple questions.
That's a great question. Let's see if I can get to there. So we, of course, were interested in answering that. The bottom line is, that was it. No. The bottom line is that the variability in organic aerosol in western U.S. is really dominated by wildfires. So it's really hard to pick it out, is the bottom line. This is some comparisons that Ashley did. This is organic aerosol concentrations at an approved site in black. Of course, we always have the issue, right, with the model simulations of organic aerosol are underestimated to begin with. But if you compare, the red line here is the simulated. Okay, so the blue line is the baseline SOA, the red line is when we increase it using the pine scenario, and the orange line is when we use the Engelmann spruce scenario. So this is what I was saying, is sort of this 1 microgram per meter cubed here. But it's really hard to pick this out from the seasonality and the variability in locations, the impacts on wildfires, and whether we have a good handle on that. So I really don't think it's something that, I think in certain regions, perhaps that are not influenced by wildfires, we might be able to start teasing this out, but it would require very careful analysis, I think, to do that. Sorry? Possibly, yeah. That could get us somewhere. Yeah.
All right. Thanks. Our next speaker is Catherine Scott.
Okay, hi everybody. So I'm going to be talking about the estimating the radiative effect of biogenic secondary organic aerosol. I'm from the University of Leeds in the UK, and so are my co-authors. And my research is funded by the Natural Environment Research Council. So firstly, I'll just quickly discuss what biogenic secondary organic aerosol actually is, and we just heard a little bit about that from Colette already. Before going on to describe how that affects the number and size of particles in the atmosphere, and then ultimately what effect that actually has or could be having on the climate, and whether that might have actually been different in pre-industrial times. Okay, so as Colette was just saying, vegetation emits volatile organic compounds such as monoterpenes and isoprene into the atmosphere. These little maps here are just to give an idea of how much of the Earth's land area is actually experiencing BVOC emissions. So they are quite an important thing for us to be able to understand. And the reason that we're interested in them is that the VOCs themselves don't hang around for very long. They're quickly oxidized into more complicated products, complex products even. And it's these products that are important in terms of aerosol, because eventually they have a low enough volatility that they're able to partition into the aerosol particle phase by condensing onto other particles in the atmosphere. But additionally, several studies have suggested recently that the oxidation products of monoterpenes in particular could actually be playing a role in the formation, the very first steps of new particle formation. So there are a lot of uncertainties associated with this entire process, but two that I'm going to focus on during this talk are the fact that top-down and bottom-up estimates of the amount of SOA generated in the atmosphere on an annual basis give quite a wide range of values. So it's really not clear at all how much SOA you actually get from a given emission of BVOCs. And additionally, as I was just saying, it's now looking possible that these organic compounds could be participating in new particle formation, but exactly how is not really clear yet. So both of these pathways will affect the number, size, and composition of the particles in the atmosphere. And one of the things to say about the fact that these oxidation products can condense onto existing particles is that they help them to grow to larger sizes and also make them soluble. So in that sense, we could be influencing the number of cloud condensation nuclei in the atmosphere and then potentially the number of cloud droplets. And so both the change to this sort of size distribution of aerosol in the atmosphere and this change to the number of cloud droplets can be affecting the climate either directly or indirectly. So in order to examine this, I've been using a detailed global aerosol microphysics model called GLOMAP, which was developed at the University of Leeds. I'm using the modal version of the model, which tracks both particle mass and number in log normal size modes. And we include within the model representations of aerosol nucleation, condensation, coagulation, deposition, and scavenging. So for these experiments, I've been including the global dataset of BVOC emissions for monoterpenes and isoprene from Gunther et al. 1995. These are oxidized in the model and produce a condensable secondary organic material with a fixed yield for isoprene and for monoterpenes separately. And then that condensable material is able to condense onto the existing distribution of particles in the atmosphere according to their surface area. So from this, we can establish how the inclusion of this source of biogenic SOA is affecting the size distribution and composition of particles in the atmosphere, and then use a radiative transfer code to determine the direct radiative effect and also the first aerosol indirect effect via the change to the concentration of cloud droplets. Okay, so what happens? This map here shows how the global distribution of cloud condensation nuclei concentration changes when we include a source of biogenic SOA in the model. So this is the annual mean, and areas that are yellow or red are experiencing an increase in CCN concentration. So you can see that vast areas of the land of the Earth are actually experiencing an increase in CCN as a result of this. This gives us a global annual mean change of about plus 13%. And the interesting thing is that most of this change is actually a result of CCN increases in the tropics, which are occurring because the condensable organic material is aging insoluble mode particles from wildfire emissions. And that actually accounts for the majority of the CCN increase. But the CCN concentration is really just an idea of the number of particles that potentially could form cloud droplets. So we use the parameterization of Nenez and Seinfeld to estimate how this would change the number of particles that actually are able to activate to cloud droplets. And this system, importantly, includes a way of calculating the maximum supersaturation from the aerosol distribution that's present. And that's important because it means that not all of the CCN will be activated. So you can see that actually the biggest changes in cloud droplet number concentration don't coincide with our biggest changes in CCN. And that's because in these regions, because there's a lot of particles already from wildfire emissions, the conversion of CCN to cloud droplets is actually saturated as a result of water availability. But what we do see are smaller changes in cloud droplet number that are occurring as a result of quite modest changes in CCN in pristine regions where the ability to perturb the cloud droplet number concentration is quite great. Okay, so these numbers are from the simulations that I just shown. So we can see that a 13% increase, global mean increase in CCN gives us only a 4% increase in cloud droplet number concentration. And I mentioned at the beginning that there's a lot of uncertainty associated with the amount of SOA generated in the atmosphere. So for this control simulation, I've used our standard yields for BVOC oxidation, and we get about 40 teragrams of SOA produced. So I thought I'd see what happened if we increased that by a factor of 5. So we're actually getting 200 teragrams of SOA per year. And you can see that the change to CCN concentration is increased, but we don't see much of an increase in the number of additional cloud droplets. And that's because of that saturation effect that I just mentioned. And additionally, so our control simulation includes a mechanism for the formation of new particles in the boundary layer as a result of the activation of sulfuric acid clusters. So I did an additional simulation where we allow the oxidation products of monoterpenes to participate in the formation rate of these clusters according to the Metzger et al. 2010 paper. And when we do that, we see a much more significant increase in CCN concentration and also in cloud droplet number concentration. And that's really because in the absence of the BVOCs in this situation, we're not seeing any new particle formation in the boundary layer. So it's kind of a double effect here that we're seeing. But ultimately, we're interested in this because we want to know how it affects the climate. So the maps I've got here are for my control simulations. So on the left, this is the clear sky direct effect. So this is the effect of the particles in the absence of clouds in the atmosphere. So the actual effect would obviously be less than this. But you can see that we get most of the direct effect over the areas where we saw an increase in the number of particles large enough to act as cloud condensation nuclei. So it kind of makes sense that that's where we'd see the greatest direct effect. And in terms of the indirect effect, we calculate this by using the fractional change in cloud droplet number concentration and perturbing the effective radii of the clouds within our radiative transfer model. And so you can see that in the areas where we were seeing increases in cloud droplet number concentration over the oceans, we're getting quite a strong first indirect effect. And that's because these areas have a lot of low-level cloud. And so what's interesting is that we actually don't see much of an effect in the regions where we were getting our greatest CCN increases. And that's because it wasn't carrying through to an increase in cloud droplet number. But also, you can see on here that I've actually got some patches of positive radiative forcing via the indirect effect. And these are the result of really tiny decreases in cloud droplet number concentration, so small that you couldn't see them in the previous plot. And they're happening for a number of different reasons. There seem to be a couple of mechanisms that are contributing to this. So one thing is that the fact that we're aging so many of our insoluble mode particles more quickly means that they don't have a chance to travel as far before being scavenged. So there are a couple of things that contribute to these positive forcings, but actually they're really very small in comparison. So for our control simulation, I was getting a clear sky direct radiative effect of about minus 0.23 watts per meter squared, and an indirect radiative effect of minus 0.11 watts per meter squared on the annual mean. But when I repeated this for the simulation where I multiplied our SOA yield by 5, you can see that actually the direct radiative effect is increased significantly. And that's because we are seeing more larger particles that are able to have an influence on the direct effect. But the indirect radiative effect isn't changed at all, and that's because we weren't really having an effect on the cloud droplet number concentration. And when I allow the oxidation products of monoterpenes to participate in new particle formation, the most interesting thing is that we now see an indirect radiative effect of minus 0.8 watts per meter squared. And I've had a look at a couple of other sensitivities within this system. And this sensitivity to the inclusion of organics in the particle formation rate is actually the greatest, it's the most important factor, really, in determining the magnitude of this indirect effect. So something else we're interested in is whether this effect would have been different in pre-industrial times. So the numbers on the first row here are the for my control simulation in the present day. But if I repeat the simulation with anthropogenic emissions from 1750 from the Aerosol database, the thing to highlight is that we see a greater fractional increase in CCN and a greater fractional increase in cloud droplet number concentration, and that's because the cleaner atmosphere allowed for a greater perturbation of the cloud droplet number concentration. And as a result, we see a threefold increase in the magnitude of the first indirect effect from biogenic SOA in the pre-industrial period. And so because of this enhanced sensitivity and the fact that in the present day, when we increase the yield of BVOC to SOA conversion, we weren't seeing a great deal of sensitivity. I decided to run a couple of extra experiments to see how the sensitivity to yield might have changed in pre-industrial period, and then calculate an anthropogenic first aerosol indirect radiative forcing under a number of different SOA yields. And this plot, just quickly, indicates that the magnitude of the first aerosol indirect effect from anthropogenic emissions is actually sensitive to the yield that we use for the generation of SOA production, because it's very sensitive to the baseline atmosphere in pre-industrial times. So in order to quantify this effect, we really need to understand exactly what was going on in the atmosphere before the anthropogenic emissions were started to go in there. So to summarize, biogenic SOA is exerting a negative global annual mean radiative effect via the direct and first indirect effects on the climate. The direct radiative effect is very sensitive to the amount of SOA generated from BVOC emission, whereas the indirect effect is more sensitive to the way in which we form new particles in the atmosphere. And we can see that the first indirect effect from biogenic SOA was more sensitive to yield changes in the pre-industrial atmosphere, making the quantification of that anthropogenic first aerosol indirect effect dependent on our correct understanding of biogenic SOA in the atmosphere. So, thanks.
We do have time for a couple of questions since our next paper was a withdrawal. So if anyone has any questions for our speaker.
Did you consider changes to biogenic VOC emissions in the pre-industrial atmosphere? What might they be and how might they affect your results?
Yeah, so sorry, I didn't mention that. In these simulations, I just used the same VOC emissions so that we could make it directly comparable. But I think in the pre-industrial, the VOC emissions, despite the amount of land use change that's gone on, weren't actually that different to today, just based on estimates in the literature, I think, that I've seen. Yeah, that's my point. I think despite that, I think there's a paper by Lathier who suggested that actually because of other things, so CO2 fertilization and temperature increase, the amount of land use change and then those factors that have increased BVOC emission have to a certain extent cancelled out. I think there is a small difference, but...
But the land use change that has occurred is cropland expansions, changing forest to crops, and crops don't emit VOCs.
Okay, yeah, I take your point. So I think in this case, it was more to try and quantify the effect of those BVOC emissions in different levels of anthropogenic emissions at the same time. But if you were actually trying to quantify the pre-industrial effect, then yeah, you would have to take that into account.
Well, thanks so much. We're going to have to take a short break and reconvene at 11:35 to stay on our schedule. Thank you.
Yes, yeah.
You know?
No, but I was at another meeting where
They did that.
They did that. It's been the transition. Like, the annoying thing is like everybody in the audience watching the speaker or the organizer try to find the little box that puts it in the slide. Right?
Were you at Naomi's speech? Oh my goodness. They had a 10-minute delay while the organizers were trying to figure out the map. They were in Reader and they were trying to open her PowerPoint, and people kept yelling, close Reader, but they couldn't figure out how to do it. It was
I missed that one on the schedule. What did she talk about?
She talked about climate communication. Apparently she had to talk earlier in the week about some recent results looking at how scientists kind of communicate and how they are more conservative in their results than you would expect, and trying to explain why.
Oh.
That they're always sort of wrong on the less alarmist end. If you look at, and apparently they went and documented that in their paper, which I haven't looked up yet.
But that's like committee reports, though, right?
No, they actually said, I think they used a climate, right? Just climate. And they basically said things like sea level rise, right? They looked in the scientific literature. That's interesting, yeah. I didn't read the paper, so I'm going to see what they actually did that, but yeah. Is overestimating, yeah, clearly. So I had a question. I want to follow up with you about RCPs. You have them in chance count. Because I keep wanting to do something with the impacts models that I have, and I'm thinking that comparing them to our own scenarios, but comparing the RCPs, actually, I think could really strengthen the paper. So if you want to collaborate on something.
Okay, sure. Yeah. Well, I've run some stuff, so we might as well get some done.
Yeah. All we need is sort of global ozone and PM 2.5.
Yeah. The thing I'm hesitant about is that it's useful to run a model and compare them to whatever models.
Yeah, and
has had big problems too.
Yeah.
There's no consistent, like different people implementing different ozone layers.
Right. So
So this has a different setting.
yeah, I want to do a sort of emission scaling. I haven't done runs in geochem. I've only done black carbon and sulfate changes using 10 watts model of the two-moment aerosol scheme. So I have changed the black carbon and sulfate aerosols. I'd like to have our emission scenarios go into geochem, but I was sort of waiting for that promised plug-and-play scaling factor mechanism that's supposed to go in the next version. Like, there's a front end to make it easier to scale emissions.
I didn't know that.
Yeah, I don't know who developed it. I should really just contact them and see if it's ready, because that was so much easier.
Yeah.
And
The RCPs are in the development pipeline.
yeah.
Actually, they told me what model version that is.
No, and it would be good. I mean, it would just be like gridded output, because I have growth that just, population weights by the regions of my impact model. So, I mean, total emissions you can get off the website, so that's pretty easy. But just to give some model comparisons might be at least useful to benchmark. Good way to break it up. And just make sure that
Partway through, but it's going to be kind of weird if I'm like up here while someone's taking off the sweater.
yeah. I was actually just thinking, I looked over and I'm like, we look so natural. Yeah.
When was that Canada? Yeah, I remember those fires. I lived in Boston at the time.
Yeah.
Mhm.
Me too.
What do we have? Is my clock slow, fast? It's time.
We can wait another minute.
One
It seems
minute.
like people are coming in, but
Yeah, I can't wait.
probably no more. Also, we need our speaker.
Oh, yeah, he's right there. So I
Okay.
think he's ready. You ready? Okay. Okay, thanks. Okay, we're going to go ahead and continue now. We'll have our next invited speaker, James Levine.
Okay, so is it right click to advance? Okay, thank you. Okay, thank you. So I'll be talking about the ice core record of atmospheric methane, chemistry-climate interactions on tens to thousands of years. And this is work that I've been doing with colleagues at the British Antarctic Survey, the University of Lancaster, the University of Bristol, and the University of Cambridge. Now, of the 800,000 years that the ice core record spans, that's 8 cycles between glacial and interglacial climates, I'm going to focus just on the last 40,000 years. And this takes in many of the major features in the ice record of methane. It includes the large glacial interglacial difference, practically doubling from around 360 parts per billion by volume at the last glacial maximum 21,000 years ago to around 700 ppbv in the pre-industrial. Now you'll note that left off this plot is the anthropogenic rise in the last couple of hundred years. The last 40,000 years also includes some of the rapid rises in methane of 100 to 200 ppbv at the beginning of Danskard-Oeschger events, occurring on timescales of perhaps just a few tens of years. Now, I want to talk about 2 model studies. The first, dubbed Sources and Sinks, focused on exploring the causes of this LGM pre-industrial change in methane. You might wonder, when I talk about a rise or a near doubling in concentration, why I've drawn the arrow downwards. And that's because when I come to the model experiments, I start from a pre-industrial model setup and explore some of the possible drivers of the reduction in concentration we see under glacial conditions. I'll then just very briefly touch on an extension of that work to those rapid rises in methane at the beginning of Danskard-Oeschger events. But the second study relates to a complementary constraint we have on past changes in the methane budget, and that's namely the carbon isotopic composition of methane that we know differed under glacial conditions as compared with interglacial ones. But starting with that LGM pre-industrial change in methane, the question at the heart of this study was, can we reconcile recent bottom-up model estimates of the changes in methane sources and sinks with the change in concentration we observe in the ice? By way of background, until recently, bottom-up model studies attributed between about 1/3 and 1/2 of the reduction in methane concentration seen at the LGM relative to the pre-industrial to a reduction in methane emissions, and appealed to an increase in oxidizing capacity driven by a reduction in non-methane volatile organic compounds emitted from vegetation to explain the remainder. And it certainly seems sensible that under glacial conditions there was less vegetation, less emissions of those NMVOCs from vegetation, leaving more OH available to oxidize methane and reduce the concentration towards that observed. But there are certain problems with this explanation. Firstly, that some of the OH that we've conventionally thought as being consumed in oxidizing isoprene, the most abundant of the bio-NMVOCs, may actually subsequently be recycled, loosening the leverage that those NMVOC emissions have on the oxidizing capacity. And secondly, basic physical chemistry, that under glacial conditions, the lower air temperatures and lower humidities would have tended, if anything, to increase the concentration of methane. The lower temperatures slowing the reaction between OH and methane, and the lower humidities, all else being equal, tending to reduce the availability of OH. Now, more recently, there's been a far greater estimate of the reduction in methane emissions from wetlands, the dominant methane source, at the LGM. Weber et al. Estimate that this is between 35 and 42%, compared with the 27% reduction estimated by Valdez et al., and effectively no change by Kaplan et al. So when we take this far greater reduction in methane emissions from wetlands, and add to that the estimates of Valdez et al. And Kaplan et al. Regarding the other sources of methane, termites, the ocean, biomass-burning, the result is a range of possible reductions in concentration, purely source-driven, at one extreme of which it's possible to explain the entire change in methane concentration through changes in methane sources alone, without recourse to any change in oxidizing capacity. So it begs the question what the net effect of these influences on the oxidizing capacity was. So we've explored this through a series of sensitivity experiments with the Cambridge P-Tomcat model. It's a global atmospheric chemistry transport model, starting from a model setup for the pre-industrial that yields a pre-industrial-like concentration of methane. And in the first experiment, we took out all of the NMVOC emissions from vegetation. Now, we don't think that there was no vegetation at the LGM or no emissions from that vegetation, but this gives us an estimate of the maximum influence any reduction in those emissions could have had. And we calculated 22% reduction in methane concentration, moving us substantially closer to that LGM concentration we observe. But when instead of changing those emissions, we just reduce the air temperatures in the model in line with the simulation of the LGM and reduce the humidities in line with those temperatures, we calculate an 18% increase in methane concentration. When we combine those changes, we get an 11% reduction. And when instead of taking out all of those emissions from vegetation, we reduce those in line with a simulation of the LGM, we calculate just a 3% reduction. And this shrinks further to a 2% reduction when we include an OH recycling mechanism based on the theoretical calculations of Peters et al. So if the net change in oxidizing capacity was negligible, and that's assuming that no other factors besides those we've explored significantly influence the oxidizing capacity during this period, I can speak more to that at the end if you're interested. It implies the entire LGM, or practically the entire LGM pre-industrial change in methane concentration was source-driven. And if you recall, that is possible at one extreme of the most recent estimates of the reduction in methane emissions at the LGM relative to the pre-industrial. So from that study, we conclude that it's plausible that the LGM pre-industrial change in methane was entirely source-driven. And we can thereby reconcile recent bottom-up model estimates of the changes in methane sources and sinks with the change in concentration we observe in the ice. Now, by way of a small extension of that study, using the simulations of Hopcroft et al. Of idealized Heinrich-stadial and Greenland interstadial states, we find that across an idealized rapid rise in methane at the beginning of a Dansgaard-Oeschger event, the influences of NMVOC emissions, air temperatures and humidities on the oxidizing capacity continue to offset each other, and the net change is very small, implying that those rapid rises in methane at the beginning of DO events were also source-driven. And that begs the question whether the ice core record of methane over perhaps the whole of the last glacial-interglacial cycle purely reflects changes in methane sources. So with that, I'd like to move on and more briefly to the second study dubbed isotopes, and specifically the carbon isotopic composition of methane. And the question at the heart of this study is, could changes in the strength of what is a relatively minor methane sink, oxidation by atomic chlorine in the marine boundary layer, have contributed to glacial interglacial changes in this complementary constraint we have on the methane budget, delta 13C of methane? Now, you might wonder, when I've just said that we think the LGM pre-industrial change in methane concentration was entirely source-driven, why we're looking at the influence of a sink on this complementary constraint. But atomic chlorine is thought to oxidize, or thereby remove, only 3 or 4% of methane globally. So it has very little leverage on the concentration of methane. But owing to the very strong preference it shows for removing 12 carbon methane instead of 13 carbon methane, it actually exerts a very strong leverage on this complementary constraint, the delta 13C of methane. So our work was part motivated by the measurements of Fisher et al. Showing that delta 13C of methane was enriched by 3.5 per mil at the LGM relative to the pre-industrial, the scales inverted. And like previous studies, Fisher et al. attributed that change in delta 13C of methane to a change in the relative strengths of different methane sources with different isotopic signatures, specifically to a near shutdown of the boreal wetland source of relatively 13 carbon poor methane in the context of not dissimilar biomass-burning emissions of relatively 13 carbon-rich methane. The problem is that just after Fisher et al. Published those measurements and their explanation for that change, there was a global synthesis of charcoal records published by Power et al. Showing that there was less biomass burning at the LGM than in the pre-industrial. So we may still have some of that enrichment to explain. And it's in that context that we started exploring the influence of this small methane sink, oxidation by atomic chlorine in the marine boundary layer, or CLMBL. Why did we pick atomic chlorine? Because its changes in the concentration of this CLMBL have been invoked to explain recent interannual variations in delta 13C of methane. We know that sea salt is a major source of atomic chlorine in the marine boundary layer, and the production of that is highly sensitive to the wind speed of the sea surface. You see powers of 3 between wind speed and sea salt aerosol production. And polar ice records of dust and sea salt may be indicative of changes in the circulation at the LGM. So we set out to do some simple calculations to explore the influence of changes in winds at the LGM on the production of sea salt aerosol, making some quite crude assumptions about how that influences the availability of atomic chlorine and its impact on delta 13C of methane as it preferentially removes the 13 carbon methane, the 12 carbon methane. Those simple calculations combine Allen et al.'s formulation for atomic chlorine concentration, Gong et al.'s wind speed dependence of sea salt aerosol production, and pre-industrial and LGM winds taken from a variety of GCMs of the PMIT2 generation. Now, in response to the changes in winds and temperatures at the LGM, we calculate changes in delta 13C of methane relative to the pre-industrial of the order of 10% of the glacial interglacial difference observed in the ice. Now, actually, that takes in everything from a 0.46 per mil depletion to a 0.14 per mil enrichment, reflecting the disagreement between the models as to how the circulation differed at the LGM. But I'd argue that 10% of the glacial interglacial difference observed is significant, particularly when you consider the multiple factors that could influence the strength of this atomic chlorine sink that we've not explored in this study. We explored the winds alone and their influence on sea salt aerosol production. But we could also explore change in the lifetime of sea salt aerosol under a colder, drier climate, less precipitation, longer lifetime with respect to wet deposition, atmospheric acidity, governing the release of that atomic chlorine from the sea salt, and even sea ice extent as there being a possible source of sea salt in the sea ice zone that dominates at high latitudes. So with that, I reached the conclusion that the size and sign of the influence that changing the strength of this minor methane sink are uncertain on delta 13C of methane, but we cannot simply ignore this in future interpretations of the glacial interglacial delta 13C record. So with that, I'll leave up my conclusions. I'd like to make these acknowledgements and thank the conveners for this opportunity to talk and invite your questions. Many thanks.
We might have time for one question.
So we haven't considered that. If I've understood you correctly, then this new information to me affects what fraction of methane might be removed by atomic chlorine globally, annually integrated. And it's true that the numbers I put up there directly follow on from the assumption that atomic chlorine removes 3 to 4% of methane globally annually. Thank you.
Okay, we'll have our next speaker, Lee Murray.
Okay. Great. If you go to the first slide. No, I'm sorry. Great. Thank you. And I'd first like to start by thanking my advisors. And so today I'm going to talk about the role of lightning on the oxidative capacity and what that might mean for climate. And my motivation slide, actually, I might have not had to even include because it's been already discussed at length during this session. But the tropospheric oxidants, ozone and OH, are a critical link between the tropospheric chemistry and climate. Ozone itself is a greenhouse gas, and OH regulates the lifetimes of many of the greenhouse gases, including methane and ozone-depleting substances, and also a lot of air pollutants of human concern. And as James just pointed out, methane in the ice core is reflecting, well, a lot of debate over the relative role of emissions and OH sinks. And as we saw in Catherine's talk, the oxidants really can influence the overall climate effect of the various aerosol particles. So it's really important that we can understand the factors that are controlling interannual variability, or IAV, in the tropospheric oxidants in the recent past if we want to make prediction about the near future. So what I'm going to talk about is the role of NOx, specifically NOx from lightning. And the amount of NOx produced by lightning is a very important precursor for both ozone and OH. And because lightning itself is dependent upon meteorology, it represents a chemistry-climate feedback. There are a lot of uncertainties in global models about simulating lightning, chief among them just putting lightning in the correct place in the world. And existent parameterizations in the literature in global CTMs really fail to reproduce the climatological observations we have from LIS and OTD, which are two satellites. This is just showing the global distribution of lightning calculated on top of geosphoret fields from three very popular lightning parameterizations out there. The long-term monthly mean for both of them, and none of them can capture even half of the observed spatial temporal variability. So what we traditionally do in the CTM world is to scale these equations locally to match the long-term means of the climatology and the parameterization. And this does fix our spatial distribution and seasonality, but it leaves any IAV up to the model meteorology. And the reason we have done it this way is because even though satellites are far more dense than, say, surface observations, they are still relatively spatio-temporally sparse. And LIS goes up and down from 35 degrees south to north, and it can be prone to sampling biases over short time scales. Particularly, lightning has a very strong diurnal cycle, so if you're not sampling over the full diurnal cycle, then you could induce artificial variability. So to address this, I've come up with a method for creating a constraint for interannual variability. The gory details are in a paper just published in JGR, but the baseline is identified within the GeoChem model about 37 regions globally using a clustering method that can statistically identically constrain the seasonal cycle of ozone as if I were doing it at the native model resolution. And these large-scale regions now greatly reduce the potential sampling biases from LIS, and I'm able to determine mean regional flash rates in that region for a given month. And so if I aggregate all those regions, I can create a tropical lightning flash rate, and this is looking at it over the extent of the LIS campaign window from 98 through the present, and we see a lot of variability. The dashed line represents a 12-month running mean, And if we compare that with the 12-month running mean of the Nino 3-4 index, we find a correlation of about 0.8. So even though there's a lot of variability regionally in the lightning variability, on average, the three major land masses in the tropics tend to be warmer during El Nino and tend to have higher lightning flash rates. So I take this lightning flash rate constraint now regionally and use it in the geochem model in order to constrain our lightning NOx emissions using an assumption of fixed NOx per yield, fixed yield per flash. And so this blue is just the traditional seasonal method, and we are able to increase with the interannual constraint the amount of variability in the NOx source. And then if we compare that with the other major global NOx sources, we see that it is about comparable now to biomass-burning NOx, which is the major source of interannual variability in NOx emissions. And so to explore the impact of this on the photochemistry, I'm going to drive a 9-year hindcast for 98 through 2006, overlapping the years for which we had geosphere meteorology, the GFED biomass-burning emissions inventory, and the new IAV constraint. So let's look at ozone first. We have long-term observations of tropical tropospheric ozone columns available from satellites since the late 70s. So this is a combination of the EPTOM CCD product and the more recent OMI-MLS product at the end. And if we're looking here at the local standard deviation of the time series of monthly anomalies to give us a metric of the spatial distribution of variability in the tropics, and there are four major regions: the Eastern Pacific, Central Brazil, the Eastern African outflow, and the Maritime continent. And this is the old method with just the standard constraint. This is the one with the new interannual constraint. And we are improving so overall, the model does underestimate the total variability seen by the satellites in ozone, but we are increasing it in the critical areas a bit. And in each of these four major regions, we are improving the correlation. Sometimes it's still low skill. South Atlantic here is included as an example of low variability. But in fact, across the tropics, the correlation locally has improved everywhere. And the biggest improvements are in these regions that have lowest skill to begin with in the outflow regions. To get a sense of how sensitive ozone is to lightning, I'm showing here Hofmuller plots. So we have longitude in the tropics on the x-axis and time on the y. So we can see there was a general negative anomaly in the first half of the period and general positive anomaly similar to the ENSO index. And if we first look at, so I'm estimating the different contribution from the different sources by comparing the simulation with one that has no lightning, no fire emissions, and then the remainder, which we attribute to meteorology. And so if we look first at fires, we see that the contribution of fires is important, but only over Indonesia during the El Nino events. And it's really localized. And locally, it tends to be dominated by the meteorological effect as well. But if we look at lightning, the impact is, so it's following the anomaly, so anomalously low into higher with the ENSO correlation off the source continents. And because the lifetime of ozone is much higher at altitude, the impact spreads more across the tropics. But still, we find that the influence of lightning is not as important as meteorological concerns, particularly that due to convective mixing patterns. So ozone was relatively buffered against the NOx changes, but if we look at the influence on OH, the story is completely different. The interannual constraint drives very large variability in relative in OH relative to the non-IAV constrained simulations. And if we look at something, recall biomass-burning had an even higher interannual variability in its source, but if I do something as drastic as turn it entirely off or turn off fossil fuels, which have large global trends in them, the impact on the OAH anomalies is relatively low. So first let's try to figure out if this is an improvement. And so traditionally because OAH is very hard to sample and it'd be futile to try to sample everywhere in the world at once, we traditionally have inferred it from relative changes in long-lived gases whose predominant sink is with OH, like methylchloroform is the gold standard. And recently, Steve Monska et al. Have come up with, or did a study that showed that since the emissions of methylchloroform have dwindled so much since the Montreal Protocol wiped them out, the uncertainty in estimating time series and variability due to emissions is very small. So it used to be models had a very hard time rectifying variability. The bottom-up CTMs couldn't reproduce the large variability implied by the observations. So now the observations have come down, and with the new interannual constraint, the variability in the model has gone up. It's still underestimating, but there are significant improvements from going uncorrelated to being, negatively correlated to being uncorrelated. But most of this uncorrelation is due to the second part where you can see all of the lines are following similar features, and this is probably not lightning driven. It's driven by other things in the model. But if we just look at this first domain, the correlation is excellent. It's 0.8 to 0.9, depending on which years you look at. So the constraint has offered improvement over matching the temporal behavior, but there is still some things to learn. So why is OH in the model so sensitive to lightning? So to address this question, I have archived all of the reaction rates in the model. And so the burden of OH is always going to be determined by relative changes in the primary production versus the loss frequencies. So these are the anomalies of OH attributed to the anomalies in the reaction rates specified. The blues represent the primary production reaction rates. The greens represent those from the Hawks recycling source. And then the warm colors represent the sinks of OH. And just to give a quick example of 1998, so late December 97, early 98 was the record El Nino. There was record forest fires over Indonesia and Borneo, which would have, so a lot more CO drove down the OH anomaly, but at the same time there was a record amount of water vapor in the atmosphere. It was a lot warmer, there was a lot more primary production. But in the end, CO went out and we had a negative anomaly. So these anomalies will add constructively and destructively to give you the overall anomaly. We notice that the production and the loss tend to be correlated with each other. And what's mostly driving this is that the ozone and water vapor on the production effect and the CO emission on the loss effect. So now if I isolate the impact of lightning by comparing a simulation with the new IAV constraint versus one with no IAV constraint, we can see how the reactions are perturbed due to just the changing in timing of lightning flashes, and you can see that the variability follows the anomalies in the lightning emissions. So the one that you would expect, the green perturbation to the Hawks recycling, is magnified about fourfold due to ensuing reinforcing changes due to the additional production of ozone in primary production, and also by destroying CO and other sinks, so reinforcing through perturbing the loss anomalies as well. And so why lightning is so efficient at this is because this chemistry is much more efficient in low NOx environments like the tropics and the upper troposphere, and also biomass burning or fossil fuels would emit CO or VOCs that would introduce counteracting anomalies, reducing the overall trend. So to summarize and pontificate, so we find that enhanced tropical lightning activity is correlated with ozone and more strongly with OH, and if we suspect lightning is going to increase in a warming world, then that would represent a negative feedback on climate. It seems like there might actually be some kind of correlation between the oxidative capacity and ENSO. We are still underestimating both the variability seen in the ozone and the OH observations, so there's still lots of work to do. but we really need to work on improving our lightning parameterizations, particularly for CCMs, looking at the chemistry-climate interactions in the near future. And until then, the global long-term lightning data sets that have begun to come online will be really useful for CTMs in determining what's controlling OH variability. And lastly, I used fixed NOx yields per flash. It's quite a lot of recent work, like by Bill Koschek, is showing there's a lot of variability in NOx yields per flash, and that could induce even more variability in OH. So with that, thank you, and I would be happy to take any questions.
So again, we'll have time for one question.
So the fact that the model isn't massively operational yet perfectly, the remaining difference, do you think is it on the source side or the sink side?
For ozone, I think it's predominantly, my sense is that it's predominantly due to errors in transport in the model. And particularly, there are places that we match ozone really, really well in the model, and those are regions that we match the convective changes really, really well, particularly the ENSO response. But in other places in the model where we have the biggest errors with ozone, it's really regions that we, for example, have negative correlation without going long-wave radiation. So there's a good chance that the model is getting the convective mixing wrong.
All right. Thanks, Lee. Okay, and our last invited speaker is Jason West.
Well, I'm really happy to have the opportunity to speak with you today, and it's the last talk before lunch, so hang in there. I'll be talking today about if we globally take serious actions to address greenhouse gas emissions and address climate change, what would be the benefits that we would see for air quality and for human health? I want to acknowledge my many collaborators involved, including many students that work with me at the University of North Carolina, also Steve Smith from Pacific Northwest Labs, Vaishali Naik and Larry Horowitz from GFDL, and Jean-Francois Lamarck and Louisa Emmons from NCAR. Okay. Our work tries to bring together two lines of research that I'll kind of describe here. On the left is what's become known as the co-benefits research. This has acknowledged that the sources of greenhouse gases are often shared with the same sources as air pollutants, meaning that if we take action to address one of those types of emissions, we very often have an effect on the other. These studies have shown, in many cases, that the air quality and health co-benefits can be substantial when the health benefits are monetized when compared with the direct cost of greenhouse gas abatement. Many of these studies have focused locally or regionally and not globally. They've tended to analyze present-day conditions rather than looking into the future as future scenarios. And none of these studies has been conducted using an atmospheric model. In fact, much of the impetus for this work in the past has come from economists and people in public health, and the contributions of atmospheric scientists and atmospheric modeling has maybe been less than it could have been. At the same, or we could say even more recently, there's been a growing and large literature about the effect of climate change on air quality. This has shown through many studies that climate change would be expected to increase ozone in the US, and we can say Europe as well. The effects elsewhere in the world are a little bit less clear. The effects on particulate matter are also less clear than they are for ozone. There's been an emphasis in this work on downscaling meteorology from the global scale to the regional scale. Again, this work has tended not to analyze future scenarios, and a few of these studies have carried the work forward to present health and economic damages. One of the things I'd like to point out with this work is that it's been generally phrased as, you know, what's the climate penalty of future climate change on ozone or PM concentrations, but we can't make climate change go away. And so maybe a different question or a more relevant question might be, if we were to take action to slow down greenhouse gas emissions and slow down climate change, what would be the benefits that we'd see for air quality? So we in this work kind of turned it around to ask that other question. So to summarize, we'll be looking in this work at 2 different mechanisms by which we can get co-benefits. The first one is what I talked about before as the first co-benefit mechanism, phrased as, if we reduce greenhouse gas emissions, what would be the reductions in co-emitted air pollutants? So we need an energy economics model to address that. And therefore, with those reductions in air pollutants, benefits for air pollution and human health. The second co-benefits mechanism would be phrased as, if we take action to reduce greenhouse gas emissions, thereby slowing down climate change, we'd be slowing down the effect that climate change has on air pollution with potentially also benefits to human health. The first of these mechanisms is immediate and local to where the action took place. The second, because it is through climate change, is long-term and global in scale. Okay. So our objective here then is to analyze co-benefits for air quality and human health to 2100 and building off of RCP scenarios through both mechanisms. So the approach that we take is to use one RCP scenario. That's the RCP 4.5 scenario. The RCP 4.5 scenario was created by first generating a reference case in what is called the GCAM Global Energy Economics Model. And then relative to that reference case is like a business as usual scenario. Relative to that reference case, climate policy is applied globally in order to get RCP 4.5. So think about RCP 4.5 as an aggressive global action to reduce greenhouse gas emissions, affecting all nations of the world and all economic sectors. So the difference between the two then is entirely due to the climate policy, and that's why we want to look at it here. So that gives us the effect of the climate policy on co-emitted air pollutants. We also then use meteorology for future years from the GFDL model, AM3. And so we've constructed a reference case scenario where we're mixing our reference case with RCP 8.5. Of course, the reference case itself was not run through a GCM, but 8.5 RCP is actually fairly close to the climate change that we would expect to see under the reference case. We do a straight run of RCP 4.5, and then we mix and match a little bit so that we can tease apart the influences of the change in co-emitted air pollutants, which I said was the first co-benefits mechanism, and the effect of the change in meteorology due to climate change, the second co-benefits mechanism. I'm running these scenarios in Mozart 4, and what we did was for each of these cases, that is year scenario combinations, we ran the model for 5 meteorological years. And use the first year as a spin-up, and then I'll show results which are the average of the 4 years that follow. We're running with fixed methane concentrations, where methane concentrations reflect changes in emissions, and we're estimated offline with a reduced form model, and we're running at 2 by 2.5 horizontal resolution. Okay. So I'll get to the global aggregate results. I'm showing here global annual average population-weighted PM2.5. I chose to show population-weighted results because that's relevant for health. And what you see is then the world gets a little bit dirtier for PM2.5 before it turns the corner and starts to become quite a bit cleaner. This time history takes a different course in different regions of the world, where the US and Europe is starting to get clean now. But it takes, for example, China and India longer before they turn the corner and start to get cleaner. So under the reference case, which is the blue one here, the world is quite a bit cleaner in terms of PM2.5 by 2100. Relative to that, then, we could say what is the effect of the climate policy that's given by the red curve here. And so the difference between the two, we can say, is a co-benefit for air quality. And that's on the order here in 2100 of about, and as well in 2050, of about 2 micrograms per cubic meter globally averaged. You can see also the scenario where we mixed and matched the meteorology with the change in emissions to separate out the two co-benefits mechanisms. And you see basically the effect of changing meteorology had really very little effect, that almost the entire co-benefit is due to the effect of changes in co-emitted air pollutants and not due to the change in meteorology. Okay. We can look at this spatially as well. This is for 2050 and for 2100, looking at the total co-benefit and then breaking that co-benefit up into the contribution from meteorology and the contribution from emissions. And you see there's very little change, even by the time we get out to 2100, when we put it on the same scale as the effect of the change in emissions. So that first co-benefits mechanism of changing co-emitted air pollutants is really dominating as the important influence. We can also look at ozone, which is shown here. Again, I've shown a funny metric. This is the global population-weighted maximum 6-month average of 1 hour daily maximum ozone. We chose to show that because that's the metric that we'll use for our health calculations. And you see, again, the world gets dirtier before it gets cleaner. In the reference case, which is shown in blue, it ends up in 2100 a little bit cleaner than it is at the present. But we see as well that there's really a pretty significant difference here of on the order of 8 parts per billion in ozone that is the result of here implementing a climate policy. We can see also that, as it was for PM, the vast majority of this difference is caused by the change in co-emitted air pollutants, that changing meteorology associated with climate change has a rather minor effect. Okay. We can look at that spatially as well. Again, the change in emissions really dominates the effect on the total co-benefit. But now we get sort of an interesting picture looking at meteorology, with some places where ozone is going up and some places where ozone is going down. So we expect, based on the past literature, that in remote places, climate change gets warmer, the world gets warmer, there's more water vapor, that's the source of Hox radicals, and Hox destroys ozone. So we expect that climate change would cause ozone to go down in remote places. Our logic is turned around here. We're looking at slowing down climate change, so ozone is going up over oceans, for example, in fairly remote places. But we see ozone going down then in some heavily polluted regions, and that's sort of consistent with past studies that have shown climate change causing ozone to go up. Ozone also goes down here as we slow down climate change in some of the tropical rainforest regions. And we can look at some of the causes of these changes. So at the bottom here is global isoprene plotted for the two different, we're running with Megan online in Mozart, giving us the biogenic VOC emissions, and I'm showing just isoprene here. And so there really is a difference here by the time we get out to 2100, as we slow down climate change, that the increase in isoprene emission is less. And that was seen in the tropical regions. But one of the really important differences here is the methane concentration itself. So by slowing down methane emissions, we really do have a big influence on ozone. It's actually hard to quantify what the influence of the methane is itself, so we can come back to that later. We took this forward then to estimate global mortality effects. These are methods that my group has used in the past to estimate global mortalities using the output of Mozart from ozone and PM 2.5, with one difference here because we're looking into the future. So we're using a database that is called International Futures, and that gives us the changes in baseline mortality rates expected over the coming century. So over the coming century, life expectancy is expected to go up. More people will be dying from respiratory and cardiovascular problems, and those are the things that ozone and particulate matter influence. So susceptibility to air pollution is expected to go up, and we're trying to account for that here. And we see differences in, so again, the world gets dirtier and then cleaner, but the difference here is on the order of 1 million deaths per year due to the cleaning up PM 2.5. A little bit less for ozone. You see, relatively speaking, this is fairly constant, but the difference, again, between the abatement case and the reference case is really pretty striking for the case of ozone. Okay. We can look at that mortality effect in different regions of the world, and I've shown a few for illustration. Europe is getting cleaner immediately, North America as well. East Asia gets a little bit dirtier before it starts getting cleaner, and then India takes until about 2050 before it starts getting cleaner. And this is just for PM mortality. Okay, so there's, of course, some big uncertainties in what we're doing, especially when we relate the model results to health, and that's I discussed some of those major uncertainties here. We've only accounted for adults older than 30 years old. The co-benefits of greenhouse gas mitigation would be greater had the reference scenario not assumed that air pollution would decrease into the future. So had we used a different reference case scenario, for example. RCP emissions do not include primary inorganics. We've also emitted possible effects of climate change on dust, on sea salt, on fires. Okay, so those are some of the uncertainties we're dealing with. So just to conclude, we expect that the global abatement of greenhouse gas emissions would bring substantial benefits for air quality and for human health. We've estimated that those would be on the order of 1 million deaths avoided per year in 2050, and on the order of 2 million or so deaths per year in 2100. We also found that the direct co-benefits from air pollutant emission reductions exceed those from slowing down climate change. This is still work in progress, and so we'll be refining these results, but what's to come is we've left out the effect of PM 2.5 on lung cancer. That should increase the PM 2.5 numbers by on the order of 20% or so. We'll be including some uncertainty ranges on the mortality outcomes, and we'll be looking to monetize these benefits so that we can compare them against the direct control cost for greenhouse gas emissions reductions. Thanks very much.
Any questions? In the back.
Two questions. First of all, when you move from the reference case to the RCP 4.5, there are two different emission models that are behind the establishment of the emission of the reactive species. Is there any coherence between them, or can some of the changes just be due to the fact that the emission models are different? My second question is, when you do the climate feedback or impact, what about the biomass-burning increase? I mean, we've seen in Europe during the hot waves, basically what changes very much was that you had a lot of fires and wildfires that started emitting things with reactive gas emission due to climate change.
Yeah, so on the first question, we were careful to make sure that we were approaching the emissions the same way. And that's why we used the reference case from the GCAM model, which is the same model that produced RCP 4.5. And then we went through the same steps of processing those emissions. So one of the complaints about the RCP emissions in general is that they were all developed by different groups. You can't compare air pollution emissions from one group with another. It doesn't come out to be meaningful. So we stuck with the same model here, and I think that is one of the important differences here. So that was your first question. Your second question about the effect of climate change on air quality. We're not certainly accounting for all of the influences that could possibly happen, and so the effect of changes on fires are neglected here. We did account for the things that are accounted for in Mozart 4, and that would include the biogenic emissions, so I showed the plot of the isoprene changes.
All right, well, thank you to all of our speakers and for a nice set of talks. Just a reminder that we have a poster session going on this afternoon starting at 1:40.